All right, so welcome everybody to our talk about the GraalVM. This is Aleksandar Prokopec. He's a researcher at Oracle Labs here in Zurich. And I'm Thomas Wuerthinger, I'm also a researcher here. And we'll do this presentation together. I'll be responsible for the demos, and Alex will do the talking. And before Alex talks, we need a little bit of a safe harbor statement here as usual. This is just research that we present here, and we are making no commitments. But we still hope that at some point this research will make it into interesting products in the future. Right, so over to you, Alex.
Yeah, thanks a lot, Thomas. So basically, thanks for coming. So this talk will be about our new runtime called GraalVM. This is essentially a language runtime, polyglot language runtime, and the goal of this lecture is basically to illustrate to you how and why is GraalVM different than other runtimes, and we're going to do this with 3 highlights that we want to point out here. First of all, the GraalVM is polyglot. Second of all, it's embeddable, and third, it's very efficient. So this lecture will be, as I said, basically this presentation will be structured through these 3 key points. Okay, so first of all, polyglot. What do we mean by this? Essentially, every once in a while, people have an idea, why don't we have one language that unites all language? Why don't we have one language that rules them all? So every once in a while on Stack Overflow, a question pops out, such as this one. When can there be an ultimate programming language? And the result of that is usually as follows. The question gets closed as non-constructive, right? And of course, there are good reasons for this. So first of all, so if we go to the next slide, first of all, the world is polyglot, right? So that means we don't have just one language, we have many languages, and there are good reasons for this. Different languages are tailored towards different parts of the software stack and are tailored for different usages. So for example, what we have here on the right is the TIOBE programming index from 2017, which uses its own metrics, which you can elaborate and discuss if they're correct, but essentially there are different ratios on how much people use different languages. So for example, in TIOBE, you have, so if you go on, so in TIOBE you have like, basically what they say is that people use Java most of all, and then after that you have C and C++, and then followed by JavaScript, assembly, PHP, and so on. So, but the point is like really there are, in this ecosystem that we're using, there are a bunch of different languages that need to work together. Okay. So what is...
Yeah, there's a big other language which...
Yeah, of course, and there is a big ratio of other languages which are not categorized like as these main ones, right? The fat tail. Okay, so essentially there is a challenge here, and the challenge is to make all these languages somehow work together, to basically make the ecosystem productive when you're using multiple languages together. And we call this challenge the polyglot challenge, and essentially the problems in this polyglot challenge are as follows. So first of all, only languages which have high industry attention achieve high performance. And the reason for that is that if you really want to have a high performance implementation of a language, you need to invest a lot of money and a lot of time into it. So a typical example of this is JavaScript, which started off as an interpreter language in the browser, but it took a really long while until the whole world started using that, and there were good use cases for implementing something like V8 to get a really high performance implementation. But there are counterexamples, such as Python, which is widely used by a lot of people, which still doesn't have a particularly high performance implementation. Okay, so that's one of the challenges. We would ideally like to have all these different languages run in high performance mode. Okay, so then the second problem is that if you have multiple languages which need to interact with each other, is that each language executes in its own little box, essentially in its own little runtime. And sometimes when these languages need to interact each other, for example, a language wants to use some functionality of another language, essentially it needs to pay a high serialization cost. So it needs to marshal the data, convert it into some textual or binary form, then send it through some interface, and on the other side, the other language needs to deserialize it, and then respond to the request in the same manner. And this marshalling can be costly. Okay, and the third problem that we want to highlight is that different languages, they have different tools. And tools are of various sorts. For example, configuring your project, setting up your build system, or debugging and profiling. And of course, if every one of these languages has different tools of different quality, then you have a problem, essentially. What you'd like to have is the same set of tools of the same quality for all these different languages, right? Okay, so here's how GraalVM essentially addresses this problem. So what I'm going to show here is the software stack which comprises the GraalVM. So what we have at the bottom of this stack is the Java hotspot virtual machine. Essentially, this is a high-performance virtual machine. A lot of time has been invested into this, but if you use just Java virtual machine as is, then essentially the only thing you can do is run Java and languages that target the JVM. So then one layer above that, we have this JVM CI compiler interface, which is essentially an interface that allows one to implement a custom optimizing compiler for the JVM. So you use like dynamic class loading, you use garbage collection from the JVM, but then you can plug in your own compiler. And in our case, this compiler is Graal. This is the compiler that we developed. And this compiler alone, allows us to run Java and Scala in high performance mode on top of the JVM. And we have additional optimizations compared to the standard hotspot C2 compiler, which make these languages actually faster. We have benchmarks to support this. We do heavy benchmarking. Okay, so now that addresses the problem of running all the languages which compile down to JVM bytecode. But if you want to run other languages, such as the scripting languages like Ruby, R, and JavaScript, you need something else. And basically, the GraalVM runtime has this layer on top called the Truffle framework, which allows one to define their own language implementations and automatically get a high-performance implementation for them. In our case, the Truffle framework comes packaged with high-performance implementations of Ruby, R, and JavaScript, which were already made by our teams. And of course, we also have Node.js. And then, in addition to that, we have another layer called Sulong, which essentially enables you to, on top of this system, run any kind of code that's compiled down to LLVM bitcode. So that primarily targets C and C++, but also all the other languages which compile down to LLVM bitcode. Okay, and in addition to that, we currently have a research prototype which we're working on, which is targeted to become a fully usable product, which is an implementation of Python on top of this framework. Okay, so one very important part of this software stack is Truffle itself. And basically, the way to think about Truffle is as follows. So when you look at your application, essentially it uses a certain software stack, and at the bottom of the software stack is an operating system. Okay? An operating system is typically written in an unmanaged language, such as C or C++. And it's written by somebody who is an operating system expert. Then at the next level, you have a traditional virtual machine, which essentially takes a high-level representation of your program, such as bytecode, and then compiles it down to something efficient. And this is written by a virtual machine expert. Typically, it's written in an unmanaged language, such as C or C++, but it can also be written in managed language sometimes. So these first two levels are sort of the traditional virtual machine API. And what Truffle adds on top is something called a guest language implementation. So essentially, the idea in Truffle is that anybody can come and provide a definition of a language, and that person is then a language developer. And this definition of the language is not given in C or C++, but it's given in a high-level language such as Java. And then on the top, you have the traditional application developer who reuses the stack below with already developed languages and can write his or her own application on top of this stack. Okay, so let's focus on this third level. Essentially, what does it mean that you can define your own language? So first of all, a disclaimer is that you don't need to do this to use GraalVM. It's only if you have at your company a language that is legacy or is developed in-house, then in that case you can provide a definition of it, and you can plug this definition into the Truffle framework. You automatically get a high-performance implementation. However, if you're using one of the standard languages, which we have already worked on, then you get the implementation out of the box. But in case you're in a position of this language developer, then essentially, to define your own language, you need to provide two components. The first component is a parser. A parser is essentially something that converts your textual representation of the program into an abstract syntax tree. And the second thing you need to provide is an interpreter. So given an abstract syntax tree, you have to say, how do you execute this program? You have to give it some semantics. So let me show you an example on this slide. So let's say you have a program which is as follows. So it says, if x is smaller than 0, return minus x, and otherwise return x. So this is an abs function, essentially. So the abstract syntax tree, which must be produced by the parser, looks as the thing on the right. Essentially, it's a tree which has an if node at the top, then on the left it has the subtree, which is the condition, and then it has the true branch and a false branch. And essentially, the interpreter would take this abstract syntax tree, and then if it sees an if, it needs to call the left subtree, which will return a Boolean. And then, depending on whether the Boolean is true or false, it calls either the first, that is the second, or the right subtree. So essentially, it's an interpreter is just a method which traverses the abstract syntax tree. And this is a minimal definition of what a language is. It's the semantics of the language. Now, this is very easy to do usually, and it's much less work than implementing the compiler which produces high-performance assembly. Okay? And this is all that a language developer needs to do in this framework. Okay? So once the language developer does this, then essentially this abstract syntax tree representation is taken by the Truffle system. Optionally, it can perform, based on profiling information, additional rewrites to optimize this abstract syntax tree. And then it feeds it into a framework, into an engine called a partial evaluator, which essentially from this abstract syntax tree and the definition of the interpreter produces a high-performance compiled code automatically. Okay, so this part on the right side of this slide is completely automatic. It's handled by the framework. Okay, and so I imagine that most people using GraalVM will not be actually defining their own languages, but in case they do, there is a template on GitHub called Simple Language, which you can take a look at, and you can extend it, or you can use it as an idea to produce your own language definition. Okay, so that's so much about polyglot aspects of this runtime. The other thing we want to talk about is that it's embeddable. And what do we mean by this? Essentially, we have built, so basically what you can do with GraalVM is that you can embed it into different runtimes. So you can take GraalVM as a binary, and you can put it into a runtime such as a database or some other program. And that means that you can, from this other runtime, directly execute code in other languages. So for example, what we've done with the Oracle database, we basically integrated the GraalVM runtime into the database so that users can write their SQL queries and directly from the SQL query call some JavaScript function, for example. And then essentially the advantage in doing so is that you don't need to query the database to get the data and then implement separate functionality on another business logic server, but you can push your business logic all the way straight into the database. And if there's a rich ecosystem that you want to reuse, such as NPM libraries, then you can directly run them in the database. And we also have this thing done for MySQL. We have a research prototype for the Nginx HTTP server, where we use GraalVM to provide users with the ability to specify custom routing rules using JavaScript. We also allow analytical queries in other languages on Apache Spark. So that's kind of the idea of how what embeddability provides you. So you can go to next slide. So the real value added by this embeddability is that if you have a bunch of languages, then you automatically can use them all together. And what you get when you use them together is interoperability. So different languages can call each other's functions directly. You get the same tooling. Essentially, if you're using a debugger, you can debug this as one application. So you can see the stack, which is composed of calls to different languages, for example. And you get the high-performance optimizations, which are shared between the languages. And on the other hand, you can embed this into different products. Okay, so how does this embedding actually work? It turns out that Graal is somewhat of a hybrid between a static and a dynamic runtime. And what do we mean by this? Well, essentially, what we talked about so far is that Graal runs on hotspot, and then on top of hotspot, it executes Java bytecode or these abstract syntax trees for other languages. So that's one mode of running Graal. So there's another mode. So we have a project called Substrate VM, or for short SVM, which essentially allows you to take your Java application and then precompile it together with this Substrate virtual machine and produce one image of the entire application. And this image is essentially a binary, program binary, which has the virtual machine packaged together with your Java program. Okay, so this is this gray area on the right. What it additionally allows you is to still dynamically execute code from these other languages, right? Okay, so go to next slide. So the first thing that we want to highlight here is that it's also very efficient. So here are just some slides. So we actually run a lot of different benchmarks. We have probably several hundred benchmarks altogether used in our development process. So here we're showing only some of them here, and we're showing geometric means across benchmark suites for different languages. So this slide is, I believe, a little bit outdated. We actually constantly do improvements. So I think right now these numbers are a bit better than the ones we're showing on the slides. Essentially, so you can see basically the red bar is showing the geometric mean across all benchmarks for the GraalVM, and the gray bar is showing the geometric mean across all benchmarks for the best specialized competition. So in the case of Java, this would be hotspot. In the case of JavaScript, that's V8, and so on. In the case of R, it's probably GNU-R, and so on. So in case of Java, we mostly use benchmarks which are traditional Java benchmarks, traditional workloads, such as the Da Capo benchmark suite, if somebody heard about this. So here, we're actually slightly better on these graphs than the standard hotspot implementation. But one thing that's not taken into account in these graphs is some more modern workloads, such as Java 8 streams, on which we actually achieve up to 2x better performance. On Scala, workloads which are comprised of more functional patterns and lambdas and pattern matching, this kind of constructs, we actually achieve up to 20% better performance. And then on Ruby and R, you see this effect of what I mentioned at the beginning, which is to say that there are no high-performance implementations contributed by the industry because basically these languages didn't get enough traction. And these benchmarks, we're on geometric average, we're like 4 to 4.5 times faster. On the very right, you see JavaScript. Here we're on this slide show performance which is 90% of that of V8, but we're getting closer and we're closing the gap constantly, right? So this other slide actually shows you some of the advantages of this zero-cost interop between the languages. So essentially, if one language calls into another directly rather than marshalling and unmarshalling the data, then it has two advantages. First of all, it can take pieces of the code from the target language in which the function is defined, and then optimize this code in the calling context of the language that is doing the call. So we can do optimizations across languages. This is one advantage. The other advantage is that all these languages run within the same process space. Basically, they have the same shared memory. It means you don't need to unmarshal this data, but you can directly access it. And what you see on this slide is essentially a benchmark in which the program is querying the database, and then the database sends it back the network packets as responses. Now, normally you would have to unmarshal these network packets, like convert them into some higher form, such as JavaScript objects or JavaScript arrays, and then do querying in JavaScript based on that. But what essentially this interop provides you is a way to create sort of a proxy around these network packets, and then query them directly without unmarshaling them. And the performance benefits of doing so are shown here. Essentially, if you use raw Node.js, then you have the red line. And if you use Graal.js, to execute the same workload. Then depending on the number of matching rows you get from the database, you get, starting from 10 rows, a 2x speedup, or if you're doing 10,000 rows, then up to 7x speedup by doing this direct memory access. Okay, so that's kind of the main part of this talk. So I'll give it to Thomas to talk about the demos.
Great, thanks, Alex. All right, so that was enough slides. Let's see some code. And so I have a couple of live demos, and we will try them from least risky to most risky. So let's start with the least risky first, which is I want to show you a little bit what you can do with the polyglot aspect, of things. And what I have prepared for this is I have downloaded the GraalVM binaries. They are freely available on the Oracle Technology Network. And I have installed them on my local computer. And for this, I have created a directory. And if we are like looking into this directory, into the binary directory of this installation, it looks a little bit like a Java installation. It has all of the binaries that a usual JDK download has. And there is a few more, however, because you can see here a node binary. You can see an npm binary. You can see an LLVM interpreter binary. You can see a Ruby binary. And you can also see an R binary somewhere. So R script and JavaScript. So those are all tools that are provided in addition. So here's R and R script. Those are tools that are provided in addition to Java. So when you install GraalVM, you really can think about you installing a polyglot language runtime that runs all of these languages at the same time. And so one of the things that's there is like Node.js. It's version 8.9. And I can use Node.js for running a simple hello world, which I have here. It's just a hello world from Graal.js. And I can start that up. And I can run here the Node.js application, which will tell me hello world from Graal.js. Okay, so that's running, but it's not super exciting because, well, why would I not run the normal Node.js? And so one of the first capabilities you get with the Graal-based version of Node.js is the ability to use Java data structures. So in JavaScript, for example, it's harder to do a big integer. You have to use a third-party library for this. They are currently discussing some changes in the standard, but still, let's say I want to use the big integer implementation from Java, which is very efficient and statically typed. Then in our version of Node.js, we can just import a Java type here, which is big integer. And then I can use it as if it would be like a JavaScript object. I can start this different version of the server. I need just one flag, which means --JVM, which will start Node.js and the JVM simultaneously. And so after this server is up, I can get my access to the Node.js again, and I get now my big integer on the screen. And I can use any of my previous Java libraries and still write Node.js. So this is one aspect of Polyglot. But Polyglot aspects don't stop there. I can mix other languages here as well. So I can start to use R now in my Node.js application. And R is very good at doing statistics and graphics with statistics. So what I do here in R is I create a little SVG graphic that creates me a cloud of points that I was randomly generating. And I can start this type of application now with --JVM, --Polyglot. So this enables the JVM-based interaction with Node.js, and it enables other languages, including Python, Ruby, and R, to be accessible.
You want to change the file, or?
Oh, I need to change the file. Thank you. I need to run server 3. So now I'm creating a request here. So this request will take a little while, the first one, because it needs to initialize 3 language contexts at the same time. It needs to initialize Node.js, Java, and R. But after some time, I get now my R plot, my SVG R plot, into my Node.js application. And the subsequent requests are faster. You see the points change based on random. So this is a very convenient way and straightforward way to combine these three languages. I just have this one file, and here I've written JavaScript, I've written Java, and I've written R. And first of all, if you would run this in separate files or separate applications, one issue obviously is performance, which is you need to serialize, deserialize anything you send across these languages. In our system, the data is not serialized, deserialized. It can directly, the R can directly access the JavaScript data structure and the other way around. But there's a second advantage just from a usability point of view. You don't need to program the serialization and deserialization. You get a very convenient interface here to access your Java from JavaScript or R from JavaScript. So that is on this polyglot aspects. And as it was mentioned, Graal also has this embedding aspects. And let me go to the embedding demo. So the first thing I want to demo here is that you can use GraalVM's ahead of time compilation to ahead of time compile Java code to make it start up very fast and use less footprint than it would if it would run on the JVM. So for this, I have a little Java program, which is here listed here. It uses some stream API to walk the files and list the directory. That's just there. And I can just compile that, and I can run this list directory Java program, and it lists my directories. Okay, that's the type of program. But the problem, of course, is in Java. If you do this type of utility, then and you run it, then well, it takes like 200 milliseconds. It's still sort of okay, but not the same as you would just type ls, for example, right? Which is the C version of this utility. And we in GraalVM, we provide a command that's called native image. So what I can do in GraalVM, I can say native image, and then I say list dir. So it's similar as with the Java command. Sorry, I need to compile with the correct Java version, because it's yes, okay. So it's similar with like the Java command, but it is taking now the main class of your Java program and analyzing the whole world, what is reachable from this main class, and creating a binary that includes pre-compiled everything that was reachable. And after some time, it then compiles everything and does all the ahead-of-time compilation. And what the output of this is this list dir executable, which is now just a normal C executable, a native executable. And I can run this one, and it has the same functionality like the list dir. And if I'm now timing this, I'm down to about 13 milliseconds here compared to if I'm timing just this is like 20 milliseconds. So that's a 20x speed up. In user time, it's even less. It's 50x speed up. So you can use this utility to ahead of time compile some Java code. There are some limitations as to the type of Java code that's supported. Meaning you need to specify all of the classes in advance. We don't support dynamic class loading. But we can also compile some more complex programs, because I mean, as a Java program, we're kind of used to this. But if I'm doing just this Java C, and I'm I'm doing this time Java C, and then I'm doing the list here, the Java, then it's taking me almost a second to compile this file, right? And this file is not a big file, it's just 15, 20 lines of code. So what we did is that we created a utility that is able to create a boot image from JavaC. So what I can do is I can do the same approach I used for my Java command line utility. I apply it to the JavaC tool, which is written in Java. And this scenario takes a little bit longer because it's a little bit more to work with, because JavaC is a more complex application. But it again does kind of the whole world analysis on JavaC and compiles it down and writes it to disk, creates an image, and has now ahead of time compiled all of JavaC. Now I have a new utility here, which is my JavaC here, which is pre-compiled, 15 megabytes. And what I have to use a slightly different compile command now, and I will explain this in a moment. Because JavaC usually wants to run on a JVM, and it uses the current boot class path from the JVM for looking up classes. We need to, because we ahead of time compiled it, and we're not running in a JVM, we need to specify the boot class path. But if I'm using now this to like compile my list here, it's like, yeah, let's just that's unbelievable, right? Let's just make sure it does something. Let's remove this guy. Yeah, so the class is not here, right? And it's there. Amazing. So and if you compare this one with the time, yeah, that's like 40 milliseconds user time, 35 milliseconds user time. And if I compare this with just the normal JavaC, it's like 300 or 400 milliseconds. So it's 10x. 10x speed up. We think we can do better in the future. We are currently working on things to improve the performance further, because at the moment we do the ahead of time compilation without any profiling feedback. But what we're currently working on is to allow you to profile your application, then use that profiling to create the better version of the ahead of time compiled image. And then the other advantage you get in this mode of Graal is actually that you can fix your profile, that you have a reliable profile on what you will get when you run this application, as opposed to the profile being kind of checked on the fly. And so we use this ahead of time compilation. Like originally we developed it just to be embeddable in these native applications like the database, like MySQL or Oracle database. But it turns out it might also be useful in other contexts. And yeah, as I said, there is some, at the moment we don't support all of Java with this thing. So if you try it on a large application, it might at the moment not work correctly, but we are interested to hear your use cases on why you would like to make use of such a technology, and are willing to work with you to resolve any issues if there are any. Yeah, this is this native image command which comes with the GraalVM download. You can and you can give it a class path. You give it a main class, and it's like Java EOT. Okay, so now let's go to the risky parts of the live demo. Well, I mean, just one quick note before we move on here. It's I can, in this ahead of time compiled image, everything is precompiled, but I can still run Graal-based languages. So I can still run some JavaScript, for example. I can still customize my application with JavaScript, Ruby, R. Because you can still include a compiler also in that image. And this is the type of image we use for embedding. So for embedding, we have a prototype that does embed Graal into the Oracle database. So we also have worked to embed it into MySQL, if you prefer MySQL. But yeah, here is the embedding in the Oracle database. And here is a Docker image that you can download for free that will run the Oracle database. You only need about 12 gigabytes of disk space, because the download is large for a complex technology. And I preloaded that, so we don't need to wait for that now. And you can then run this as a Docker image. You will get the version of the Oracle database. And I'm here logged into the Docker image. Yeah, I'm logged into this Docker image. And what I can do now is I can run a Node.js module inside my Oracle database. So one of the Node.js models I want to show you here is Validator. Validator is a Node.js model for validating emails and other properties like mobile phone numbers. And it has a very complex logic to validate emails. It's not like one regular expression. There's like 20 lines of code that validates emails of all sorts. And the way it works is, well, you import this and then you ask it, is something an email, and it says yes or no, right? So what I did before is I installed this npm module. And the other thing I can do here is I can deploy this as npm module. So we have a tool here that's we call dpgs. And then I can deploy this validator into the Oracle database. And it tells me some of the functions it created inside the Oracle database here. This is PL/SQL. I'm not familiar with PL/SQL, but it's kind of the typed versions of the JavaScript that we have created. But the most important thing is that we have our isEmail function here somewhere, which is here. Yes, created an isEmail function inside my Oracle database, and this isEmail function will run this Node.js model. So I can now log into this with Scott Tiger. All right. And what I've prepared here is a little superheroes table. Yes, with 5 superheroes in it, with emails and phones. And now I can just use my Node.js model in the query. So I can say select email, and then I want to validate whether something is an actual email address or whether somebody was cheating here. And I can do validator.isEmail of email from superheroes. Yeah, now I get the email addresses, and here it tells me, yes, this was a valid one, this is not a valid email address, this is also not a valid email address, and this is a valid one. So instead of kind of coming up with your own regular expression for email or not and whatever, you just use the Node.js model and be done with it. And I have a second example here, because there's Node.js models for everything. This validator, by the way, has about 1 million downloads last week, so it's fairly popular. There's another Node.js model which has even more downloads, which is called fast-Levenstein. It is a Node.js module for checking the distance between two words. I don't know why everybody's using it, maybe to be annoying when you get a new password. Kind of looks like your old one. And so here this fast-Levenstein, this has a get function which calculates the Levenstein distance between two strings, which means, well, this is 2, I need to change 2 characters. It also supports Chinese, obviously. And yeah. And so I did the same thing as with the validator. So I downloaded that and I just deployed it into the Oracle database. And now I have this get function available to me, which will calculate me the Levenstein distance. So I can now select, and now I want the name, and then I want the Levenstein distance between Duperman and the name from my superheroes table. Here we go. Okay, now we see that Duperman is close to Superman, it's reasonably close to Batman, Spider-Man, definitely not Flash Gordon. So yeah, so again, I used a standard Node.js module. I deployed, I installed it, I installed the types for it, because the types are important to have, because SQL and the database is a typed environment. And then I deployed this model with a simple command into the Oracle database, and now I can call out to this type of functionality. And you can also deploy your own code there. Of course, there's pros and cons to putting logic inside database versus outside. And but I think like one of the things that we provide you here is you actually don't need to make a commitment up front where you put your code. because we provide you an environment in which you can run your Node.js models outside the database or inside the database, and it's exactly the same environment. So you can, if you feel like, well, I want to use this utility also inside, I can do it, but I can use the exact same code. It will be the exact same engine. And the research that we're currently doing in this area is to allow some amount of auto deployment into the database, meaning I have a client application that runs a query, but then I want to ship a function into the database. So this is currently not supported, but this is kind of the research direction we are going in here, such that you, and the whole goal here is kind of to avoid also network round trips, and to avoid copying data, and to avoid copying data out of an environment where it's secure and nicely stored and managed. And this is what GraalVM gives you here. It's an Oracle database example. We are working on a MySQL integration as well. So there will be a MySQL plugin released very soon on this. And we have some prototypes for integration into other data processing engines like Spark or Nginx, as you had it. All right. Yes. So that was the demo part. And now we get to the final slides. Alex.
Okay, so to conclude, so we want to tell you a little bit about our community that we're kind of working actively to build. So essentially we have currently OpenJDK mailing list for Graal, but we will soon switch to new mailing lists which will be free as follows. So we'll have GraalVM-dev for people who are actively contributing to GraalVM, which is open source. So we have GraalVM users for people asking questions or asking for new features, and there will be a mailing list called GraalVM Announce for announcements. So basically Graal is divided, so there are two versions of Graal. One of them is open source and is available on GitHub, so you can take a look. Opening issues is very welcome, as well as submitting pull requests if you want to help us. We also have an enterprise version of Graal, which is essentially just an extension of the open source Graal, but it has some additional features and optimizations. It's actually available on the Open OTN network from Oracle at this link, and there's one release every month. So it's free to download and use, but if you're using it in production for commercial purposes, then you have to have a license. But you can evaluate it as much as you like. But as for the open source version, like if you have contributions for us, that would be great. Or just feature requests, that's already means a lot to us. We also have this link here for database integration binaries and the documentation at the bottom. And so to conclude basically this talk, one thing that we'd like to get from you here at this event, and you can approach us now in the question route or either offline, whatever works for you. But essentially what we want to learn from you is what kind of languages are you using at your company? What kind of combination of languages would you like to see? What are the use cases for embeddability that you see, or any other features that you'd like to see when it comes to interop, or any other ideas that you might have for us? So your feedback is very welcome. So thanks a lot for coming here and for listening to us. We'll be happy to take questions.
Thank you.
I have a question about the Polyglot feature. When you run different languages or different libraries of different languages on the GraalVM, how do you deploy them? Do you have to deploy the source code, which is then dynamically compiled, or can you deploy some type of precompiled bytecode? Or I didn't really get that, how that feels, how that works in practice.
Understand? Yeah. So the question is how do you deploy your code in such a multilingual environment? And I mean, a lot of the languages that you're supporting here is like Ruby, R, JavaScript. Those are languages where people typically deploy the source code. And this is what we do here. This is also what we do when we deploy the JavaScript source code into the Oracle database. For Java or similar, we support running it on bytecode. And for static languages like C, C++, the deployment model is that you are deploying LLVM bitcode. So you're deploying a platform-independent bitcode. And this bitcode is then run by our engine. So the answer basically is depends on the type of language. Dynamic language is source code, JVM-based language is bytecode, and LLVM-based language is bitcode.
Sort of our goal is to mimic the normal thing that developers do, right, in their workflow. Right?
Yeah, we try to be as close as possible to wherever the developers usually would be used to.
How well is the IDE integration? I mean, like when you work with different languages in the same file, you have auto-completion and all that stuff.
Right.
Which IDE you use?
Yeah. So the question is, how is the Polyglot IDE integration? So, I mean, we're using here multiple languages in one file for the demo. I mean, frankly, honestly, if you do your own Polyglot application, you would usually avoid using a lot of mixture in one file. You would rather do it over several files. So you would have an R file and that loads a Ruby file, and the glue code would be rather small. We don't think that it makes so much sense to combine them in one file except for the demo here. We do support major IDEs. We do support also major debugging protocols. What I didn't show in the demo this time is the debugging in the Chrome browser. We can integrate with Chrome DevTools, and that's a shout out to the Chrome DevTools team. It's awesome that they made it language agnostic, meaning we can actually debug R Ruby in the Chrome DevTools, which the Chrome DevTools developers probably don't know about. Don't tell them.
Don't tell them.
But that's awesome. So and other ideas, like, I mean, I used your Visual Studio Code for the demoing and IntelliJ and but also like NetBeans or Eclipse. They all have, at least they support all languages within one environment. And not necessarily within one file, but within one environment. But one of the things we can do in the Chrome DevTools, for example, is to debug across languages. So debug like from one language to the other. And so that is something that's nice, because we can have a stack trace that is multilingual. That works in the Chrome DevTools and also works in a NetBeans plugin that we created.
Also, one note about the support in the same file. Actually, IntelliJ Enterprise Edition has very strong support for this out of the box. So if you write like a string, which is actually a Ruby string, you can click on symbols and it takes you to the definition point. It's quite smart already.
Yeah, I guess the IDEs will catch up once this gets more mainstream.
Thank you. It's always very exciting to see what you're doing with Graal. I have an obligatory question, since you mentioned Scala. I was wondering if you tried to build a precompiled image of Scala C.
Yes. The question is if we did create a precompiled image of Scala C. Yes, we did. I think actually we're successful in doing that at the moment. Also, we cannot support all features. We also got some interest, and we will work with, there's this startup that does a faster Scala compiler.
They do the Hydra compiler, right?
Hydra compiler, yes. We are also in contact with them, so they can use this technology. But at the moment, there are some features of Scala C that also require complex reflection, so it's not an out-of-the-box application. But I'm very much assuming that we'll be able to do that within a reasonable time frame. I think we will see Java C ahead of time compile with this stuff, right? And we can compile Scala. We can also compile Kotlin. We have another small demo where we are compiling these languages ahead of time compile as well, which is kind of interesting because there is a project that's called Scala native. There's a project that's called Kotlin native. So yeah, so we have Graal native, which is Java, Kotlin, and Scala, everything at the same time. And we think actually that we should join forces with this together to support this native compilation across all languages and not isolate the languages again in their own native compilation infrastructure.
We have 60 seconds.
Okay, I will be fast.
Can we dream? Can we dream of having a full-blown web application natively compiled with the JVM, put into Docker, starting up in 5 seconds instead of 2 minutes?
Yes, absolutely, absolutely. So we have a demo also with Docker images where we are running a simple web server with Java, and where we can show that we can start this simple web server that's written in Java in 10 milliseconds or less than that even. And no, we're absolutely working in that direction. We're also doing work with the FN project from Oracle. Oracle has this FM project where they deploy function as a service, also based on Java, where we apply that. So, I mean, of course, it will take some time until we resolve all of the limitations of the substrate VM approach. But that's why we are actually, looking forward to hear from you also on what limitations we need to prioritize next, and what would make most difference to you. And it's not just the startup. It's not just the startup that's better. The other thing that's better is the memory footprint, because you're using less metadata and less profiling data when we run these applications, and this is also very relevant when you deploy several containers. Absolutely, that will happen. I'm very optimistic, and I'm looking forward to getting input and feedback from you in terms of example applications, because we are like a research lab. You know, we make up stuff, but we're not like real world people, so to speak. And so that's why we're looking for real world people to tell us what's relevant in the real world, what directions we should go, what will make a difference for you. All right, with that, thank you very much for your attention, and looking forward to hear from you. Thank you.